Let me give you an example wherein the rate determining step is not mentioned. See this. 2O3 gives rise to 3O2. This is the overall reaction. The mechanism given here is O3 gives rise to O2 plus O. Then O2 plus O gives rise to O3 again. Now this O3 plus O, another O, finally give rise to oxygen. Okay. See, in this case, you are not given any information about what the slow step of the reaction, or what the fast step of the reaction is, or the equilibrium step of the reaction is. Nothing is mentioned. Now, in such a case, what has to be done? Let us solve this out. We have to actually get the rate expression or a rate law, of course, from that the order of the reaction. Now, as usual, 2O3 gives rise to 3O2. From this, see, it can be written as a rate is equal to minus 1 by 2 d concentration of O3 by dt, right? Plus 1 by 3 d concentration of O2 by dt, right? So that is how the rate with respect to O3 and O2 can be given. Now, from the mechanism, we can give things like d concentration of O3 by dt. Look at this. You got O3 in the first, second, as well as in the third step, right? Say in the first and third steps, it is onto reactants side. Of course, it is reacting. Whereas in the second one, it is farming onto the product side. Now, let me show you that in a proper way. When reacting, no doubt the concentration goes on decreasing. So minus K1 plus, sorry, K1 into O3 plus K2 into O2 into O. Oh, okay. K2 into O2 into O. There's some problem with my internet, so I was checking. Plus K2 into O2 into O, because in the second step, it is being formed from O2 and O. In the third step, it is reacting. So again minus K3 into O3 into O. Isn't it? So this is with respect to ozone. Now let us take oxygen into consideration. I mean D concentration of O2 by dt. Come on. O2 in the first step is being formed, even in the third step. But in the second step, it is being reacted, or it is undergoing a reaction with the nascent oxygen. I mean the intermediate, isn't it? Nascent oxygen is the intermediate here. So dO2 by dt can be written as, come on, you are getting it from O3 in the first step. So positive. Concentration goes on increasing. In the second step, it is reacting. So minus. And finally, in the third step, again, you are getting it. K3, of course, you are getting it from O3 and O. Okay. So this is how we can give dO3 by dt and dO2 by dt. Now look at the things. Let me just write the things here. Of course, known things, but still, minus refers to the thing that it is reacting, plus refers to the thing that it is forming, for clarity's sake. Okay. Now, considering the steady state, see at steady state, as we know, the concentration of the intermediate by dt is given as equal to 0. Gave it just now. Now, this d concentration of O by dt, of course, can be given as, again going back to the mechanism. See, it is formed in the first step as per the mechanism and is reacting in the second and third steps. Okay. So that can be given as formed in the first step from ozone. So plus K into O3. Then in the second step, it is reacting along with O2. So this can be written as minus K2 into O2 into O. In the third step also, it is reacting along with ozone, O3. So minus again, O3 into O, right? So this can be given as equal to 0 as per the steady state approximation. It is given as 0. Now, see from this, it can be written as concentration of O, dO by dt. Concentration of O can be given as, I mean, the intermediate. This is what I was telling. Concentration of the intermediate is written considering the steady state. That's what we are doing. Okay. So it can be written as K1 into O3 by the remaining two. K2 into O2 into O plus K3 into O3. Right? Now, let us substitute this in dO3 by dt expression. Okay. Substituting this in dO3 by dt expression, what we have written right at the beginning after the rate expression. What do we get? Now come on, dO3 by dt We have actually given it as minus K1 into O3 because it is reacting in the first step. In the second step and in the third step, we got this oxygen reacting, nascent oxygen reacting. So let us take that as K2. Of course, O3 is formed in the second step, reacted in the third step. So here it will be positive, but plus K2 into O2 is what we have. Hope you remember. Then you got O. Now this O is what? Okay, if you want, I'll write it again and just show what actually I'm going to do. K3 into O3 into O. This is the expression that I'm going to take into consideration, and here I'll be actually substituting this here as well as here. Okay. And as you remember, the first and third steps are those in which O3 is reacting, whereas in the second step, it is being formed. Come on. So everything is going on smoothly. You be little cautious. Now, see, on substitution, we get dO3 by dt is equal to minus K1 into O3. Keep it as it is. You don't have any intermediate term here. But in the second step, we got plus K2 into, of course, O2. And now the nascent oxygen comes into picture. That can be given as, come on, K1 into O3 by K2 into O2 plus K3 into O3. So this is our nascent oxygen thing. And plus we also got K3 into O3 into again the same thing. K1 into O3 by K2 into O2 plus of course K3 into O3. The same thing again, because this again is your nascent oxygen term. The concentration of the intermediate. Okay. Now from this, we can actually simplify this again now. And it can be written as minus K1 into O3. Keep it as it is. Now this, of course, this last one is also negative, right? This is again minus. Minus K1 into O3. First term is minus, second term is plus, third term is also negative. So it has to be minus here. And now minus K1 into O as it is. Coming to the second step and third step, see in the denominator, we got the same thing, right? So let us take it. So the LCM can be given, of course, this. Now coming to the numerator, we got K1 into K2 into, of course, this O2 into O3, right? Minus, of course, K1 into K3, isn't it? This K1 into K3 into O3 square Okay. Hope everything is going on smoothly. Come on. Considering this and writing the final expression, it can be written as minus, yeah, let me just go with the final expression, 2k1 into k3 into O3 square by k2 into O2 plus k3 into O3. So this, of course, is our deconcentration of O3 by dt. Okay. Now let us take this 2 onto this side. So that will give us minus 1 by 2 d O3 by dt. This, of course, is nothing but rate from the first step. So that can be given as K1 into K3 into O3 square by K2 into O2 plus K3 into O3. Okay. So that is a final step. Now let me give you two more important points. Point number 1, because they have not mentioned the rate determining step, supposing if third step is the rate determining step, then these are going to be the rate constants, isn't it? K3 will be much less than K1. Similarly, it will also be much less than K2 also, if the third step is rate determining. If not, supposing if some other step is rate determining, then it will be likewise. Okay. K3, of course, if at all is, I mean, say this point is given because if K3 is much less, then you can actually neglect this area in the denominator. If the third step is rate determining, then in the denominator we can neglect the K3 term. So that is the reason why it is given. Okay. So check this out. This is very interesting. Yes. Let us now go for collision theory of reaction rates. Okay. See, it was proposed by Arrhenius. Actually, to explain why the yield of most of the reactions is very much less from the expected one. Let me say why the actual yield of most of the reactions is very much less than what is expected. Let us see. You know, chemical reactions are actually due to the collisions between reactant molecules. But you know, if each and every collision gives us the product, then every single reaction would have given us 100% yield. This will never happen. Every single collision that takes place between the reactant molecules does not lead to the formation of product. Okay. What are the criteria which give us information pertaining to what all are the collisions that lead to the formation of products? Yes, of course, there are two things which determine whether a particular collision leads to the formation of products or not. Two criteria tell us whether a particular collision leads to the formation of products or not. Now, the two criteria are, the first one is energy criterion, and the second one is orientation criterion. Okay. Energy and orientation are the two things which decide whether a collision leads to the formation of products or not. So let us first see information about the energy criterion. For that, let us consider a graph. Potential energy is plotted against reaction coordinate. Now this is how it will be. Now this is where the reactants are placed, and this is where we got our products. You know, the energy of reactants is greater than the energy of the products from this reactants and products. So this of course, is exothermic. Okay. Now, see, the reactants actually have to cross over this energy barrier placed between the reactants and products. In fact, this energy barrier determines the threshold energy, the minimum energy required to be possessed by the reactant molecules for their collision lead to the formation of products. Minimum required. But see, the reactants are here. And in order to reach or to cross over this energy barrier, they have to be given extra energy. Now, this extra energy, what is to be given to the reactant molecules is called activation energy. And in general, the energy that is possessed by the reactant molecules or the normal colliding molecules is called average energy. So, it can be given as activation energy is equal to threshold energy minus average energy, or the energy that is possessed by the normal colliding molecules. Then how do the reactant molecules get this activation energy? Acquire during the collisions. Say during collisions, some molecules gain energy and some other lose energy. Let me give you that. Suppose two molecules are reacting. One molecule gains energy and the other one loses. Molecule that has gained energy is said to be activated. Okay. Now only these activated molecules, I mean the collisions that occur between these activated molecules lead to the formation of products. Such collisions which lead to the formation of products are called activated collisions. Or you can say fruitful collisions. Okay. Or, of course, effective collisions. Okay. Generally, those which take place between the activated molecules lead to the formation of. As far as the energy criterion is concerned, collisions that take place between the activated molecules lead to the formation of products. But as we know, it's not just the energy criterion that is going to decide the fate, but even the orientation criterion also has to be taken into consideration. Coming to the orientation criterion, even the activated molecules while colliding have to approach in a head-on manner Okay, let me show you that. This way. If suppose the reactants approach each other in a head-on manner, I mean to have a head-on collision, then only you get the transition state. You can say the energy barrier or the transition state, wherein the bonds are broken. I mean, the old bonds are broken and the new bonds are formed. Okay. A transition state is formed. Then finally, you get the products. Which of course move away. Okay. Only if they approach in this kind of a manner, you get the products. In a head-on manner, you get the products. If they do not approach in a proper orientation, then we are not going to get the products. Suppose if you consider this going in this direction, let this be now look at this. Of course, this is going in this pattern and this one is going in this pattern. Okay. If that is the case, even if it is like this also, it is not going to lead to the formation of products. It has to be a proper head-on collision. Okay. So here you will have no reaction. It's not a head-on collision. Okay. Now, let us say the same thing in a mathematical way. Consider a reaction consider a reaction A plus B gives rise to products. Okay. Now, normally the rate expression is written as rate is equal to K into A into B, right? See, the rate can of course be given as Z into F into P. What are these? What do you mean by Z? You know, Z refers to collision frequency. Nothing but the total number of collisions taking place in a unit time and in unit volume. It actually covers the total number of collisions. But no, you cannot simply say that rate depends only on Z. Then what is F? You know, F actually gives us the fraction of collisions taking place between molecules possessing energy equal to or greater than threshold energy. So this is F. Now this F can be given as e power minus EA by RT. Okay. Then this P actually refers to collisions